when you think about watching a total solar eclipse, it's just, wow, that sudden darkness, everything goes quiet. Maybe you see the sun's corona.
It feels almost otherworldly.
Exactly. And then poof, it's over. So fleeting. Or like a lunar eclipse, watching the moon turn that deep red color. It seems so random almost.
But it's not, is it? That's the amazing thing. They're predictable down to, well, incredible accuracy.
Right. Which makes you think, okay, what's the math behind it all? This whole cosmic ballet happening right on schedule. It's like this perfectly calculated race against time.
And welcome back, everyone. In our last deep dive, we sort of set the stage for this, didn't we? We looked at Aryabhata's Golapāda and the basic conditions needed for an eclipse.
Yeah, the alignment, the phases being near the nodes, all that groundwork.
Exactly. And we also got into how to figure out the size of Earth's shadow way out where the moon is. That canvas for the eclipse, you could say.
So that was episode 31, nailing the why and the how big. Now we're diving into the how long and how much. Like, how did Aryabhata figure out the duration, the partial bits, the total bit, or the ring of fire?
And the magnitude, too. How much of the sun or moon actually gets covered up.
Yeah, the key stuff that makes one eclipse different from another. So we've got the stage set. Now we're looking at how the moon or the shadow kind of paints across it over time.
Precisely. And to do that, to get the timing and the drama of it all, we need to look at how Aryabhata defined some key geometric ideas based on how big these things look from here on Earth.
Okay, let's unpack that. Verse 41 in the Golapāda you mentioned gives us two really important terms, Sthityardha and Vimardārdha. They sound a bit complex.
They do, but the concept behind them is actually quite elegant. Verse 41 basically says, look, take half the sum of the diameters of the thing doing the eclipsing and the thing getting eclipsed. That gives you a radius related to the whole eclipse duration.
Okay, half the sum of the diameters.
And then take half the difference of their diameters. That gives you another radius, and this one relates to how long the totality or annularity lasts. These are the building blocks.
Got it. Let's break down the first one. Sthityardha. Sthityardha. How am I doing?
Pretty good, Sthityardha.
Okay, so half the sum of the diameters. Now, who's eclipsing who?
Depends on the eclipse, right?
Exactly. For a lunar eclipse, it's Earth's shadow eclipsing the moon. So you'd sum the apparent diameter of the shadow and the moon's diameter.
And for a solar eclipse?
The moon is eclipsing the sun. So sum of the moon's apparent diameter and the sun's apparent diameter.
Okay, so the Sthityardha radius, what does it actually represent physically?
Think of it as the absolute maximum distance the centers of those two bodies can be apart for any part of the eclipse to happen. Like from the very first moment they seem to touch.
First contact.
It's the very last moment they separate, last contact. It's the radius defining the entire interaction zone. If their centers, even at the closest point, are further apart than Sthityardha, you just don't get an eclipse, period. Okay, so it's the threshold, the minimum requirement for anything to happen at all. Makes sense. Now, the second one. Vimardārdha. Vimardārdha.
Perfect. Vimardārdha.
This one's half the difference of the diameters. Specifically, the eclipsing body's diameter minus the eclipsed body's diameter, then halved. Assuming the eclipsing one is bigger, I guess?
That's the usual case for totality, yes. Or more generally, half the difference between the larger apparent diameter and the smaller apparent diameter involved.
Okay. And what does this radius tell us?
This one defines the condition for full immersion, totality in a lunar or solar eclipse, or that ring of fire in an annular eclipse.
Ah, yeah.
It represents the maximum distance their centers can be apart for that total or annular phase to occur. If the moon's path doesn't bring its center closer to the shadow's center or sun's center than this Vimardārdha distance,
then you only get a partial eclipse. No totality, no ring.
Exactly. It won't be fully submerged, so to speak.
So Sthityardha is like the boundary for the whole swimming pool, and Vimardārdha is the boundary for the deep end where you can actually go fully under.
That's a great analogy, yeah. Sthityardha covers the entire event, first splash to last ripple. Vimardārdha defines that period of complete coverage or the central ring.
It's pretty amazing that these two values, just based on apparent sizes, unlock so much about the timing.
It really is. It shows a deep geometric understanding of the setup.
Okay, so we have these two rulers, Sthityardha and Vimardārdha. How did Aryabhata actually turn them into a duration, a time? You mentioned the Pythagorean theorem.
Yes, exactly. Something we know from his Golapāda section he was very familiar with. Imagine a right-angled triangle.
Okay.
For the total duration calculation, the hypotenuse, the longest side, is our Sthityardha radius.
Got it.
For the total or annular phase duration, the hypotenuse is the Vimardārdha radius.
Makes sense. Use the ruler relevant to the phase. What about the other sides?
Okay, one of the shorter sides, one of the legs, represents the moon's celestial latitude at the midpoint of the eclipse. The term used is Vikṣepa, Vikṣepa.
Vikṣepa. So latitude. You mean how far north or south the moon is from the ecliptic, the sun's path?
Essentially, yes. It's the minimum separation between the center of the moon and the center of the shadow or the sun during the eclipse, how far off-center the pass is.
So a bigger Vikṣepa means it's more of a glancing blow.
Exactly. A smaller Vikṣepa means it's closer to a dead center hit.
Okay, hypotenuse is the radius, one leg is the Vikṣepa. What's the other leg of this triangle? What does that represent?
That other leg is the key to the timing. It represents the distance the moon travels relative to the shadow or sun center during half of the eclipse phase we're looking at.
Half the distance. Why half?
Because the eclipse is generally symmetrical around the midpoint. The distance traveled from first contact to mid-eclipse is the same as from mid-eclipse to last contact. So this leg gives us that half path length.
Ah, okay, I see it now. So verse 42 then uses Pythagoras to find this half-path length for the whole eclipse.
Correct. The theorem tells us hypotenuse squared equals legs squared plus other legs squared. So to find the half path squared, we take Sthityardha squared, hypotenuse, and subtract Vikṣepa squared, one leg.
Right, so half-path squared, Sthityardha radius, Vikṣepa, and then you take the square root.
Precisely. Half path, a square root of Sthityardha radius Vikṣepa.
And that formula itself shows why Vikṣepa has to be smaller than Sthityardha, right, if it's bigger.
The value inside the square root becomes negative. You can't take the square root of a negative number in this context. It means there's no geometric solution, no overlap, no eclipse. The math confirms the physical condition.
Cool. Okay, so now we have this half-path distance, probably in some angular unit like degrees or arc minutes. How do we get time, like minutes or hours?
That's where motion comes in. We need the relative angular speed. The term used is bhukyantara, bhukyantara.
Bhukyantara. Relative speed.
Yeah, think of it as how fast the moon is catching up to the sun for solar, or moving through the shadow for lunar, as seen from Earth. It's the difference in their apparent speeds across the sky.
Okay.
So you take that half path length you just calculated, which is an angular distance, and you divide it by this relative angular speed, bhukyantara. Distance divided by speed gives you time.
Right, standard physics.
Exactly. And now the verse also mentions multiplying by 60. This is likely a unit conversion thing. Aryabhata's units for angles and time were different from ours. Maybe converting something like degrees per day into arc minutes per nanaka, a traditional Indian unit of time, about 24 minutes.
Oh, okay. To get a practical time unit.
Yes. And the result of this calculation, the Sthityardhanika Sthityardha, is the time taken for half the eclipse, from start to middle or middle to end.
So you just double that to get the total duration as the entire eclipse event.
That's the idea. It's a really elegant link between the geometry of the sizes, the geometry of the path using Pythagoras, and the kinematics of their movement.
Wow. And I assume verse 43 does the exact same thing, but for the total or annular phase, just swap in Vimardārdha.
You got it. Same logic, different radius. The formula becomes half path for totality equals square root of Vimardārdha Vikṣepa.
And again, if it comes bigger than Vimardārdha.
No totality or annularity. The math gives you an impossible result, correctly reflecting reality.
And then you divide that totality half path by the same relative speed, bhukyantara.
Yes, divide by the relative speed, probably do the same unit conversion, and you get the duration of half the total or annular phase. Double it for the full duration of that central phase.
That is remarkably clever, using just apparent sizes, the moon's latitude off the ecliptic, and their relative speeds to predict not just if an eclipse happens, but for how long the partial part lasts, and even how long totality might last.
It's a testament to the power of their observational skills and mathematical models. But duration is only part of the story, isn't it?
Right. How much does it cover? That's a big part of the experience.
Exactly. And that's the magnitude, or Grāsa Grāsa, which Aryabhata tackles in verse 44.
Okay, Grāsa. How do you quantify all that? The amount of coverage at the peak.
Well, the core idea is about the maximum overlap at mid-eclipse. Think about how deep one circle goes into the other at their closest point.
Okay.
Verse 44, especially when you read it with help from later commentators who built on Aryabhata, gives us a way to calculate this depth. You take the Sthityardha radius, remember, that's the radius defining any interaction.
The big one, yeah.
And you subtract the minimum separation, which is that Vikṣepa, the moon's latitude at mid-eclipse.
So Sthityardha minus Vikṣepa That difference tells you how much the circles are actually overlapping at the closest point.
Precisely. It's the depth of the intrusion, if you like.
Okay, that gives us a depth.
Mhm.
How does that become magnitude, like a fraction or percentage?
Good question. You take that overlap depth you just calculated,
Sthityardha minus Vikṣepa.
right, and you divide it by the apparent diameter of the body that's being eclipsed. This is a key point clarified by later commentators.
Ah, so not just any diameter, but the diameter of the thing being covered.
Exactly. So for a lunar eclipse, where the moon is eclipsed, the Grāsa calculation looks like Sthityardha radius Vikṣepa, moon's diameter.
Okay. And for a solar eclipse where the sun is eclipsed?
It would be.
It's the...
Sthityardha radius Vikṣepa's sun's diameter.
And what do the results mean? Like if you get 0.5?
That would mean half the diameter of the eclipsed body is covered at maximum eclipse. A magnitude of 1 means it's fully covered along its diameter.
And what about total eclipses? Can it be greater than 1?
Yes. If you get a magnitude greater than 1, it means the eclipsing body, like the moon in a total solar eclipse, or the shadow in a lunar one, appears larger than the eclipsed body, and the overlap is deeper than the eclipsed body's diameter. That signifies totality or annularity.
So the magnitude number tells you not just if it's total annular, but gives a sense of how deep into totality it goes, in a way.
Kind of, yeah. It's a quantitative measure of how dramatic the peak of the eclipse will be.
It's just, it's really impressive how these geometric ideas translate into such practical, predictive results for these huge cosmic events. It really makes you appreciate the astronomy they were doing back then.
It really does. You have to think. They were working mostly with naked eye observations, meticulously tracking positions over years, figuring out these apparent sizes and speeds.
Yeah, the dedication involved.
Just wow.
And these calculations beautifully weave together geometry, like using the Pythagorean theorem, which they called padam for a side and mulam for square root,
Right.
with arithmetic and kinematics, the study of motion, through that relative speed, the Vikṣepa,
All within this framework of a spherical Earth and predictable celestial movements.
And the craziest part, maybe, is that this fundamental approach, it's still relevant today, isn't it?
Absolutely. Modern astronomy, of course, uses incredibly precise data. We know the orbits, the sizes, the speeds down to amazing detail thanks to centuries of observation, powerful telescopes, radar, satellites.
And much more complex physics, Newtonian gravity, relativity.
For sure. We account for tiny perturbations, the non-spherical shapes of bodies, the atmosphere's effect, all sorts of subtleties. But the fundamental algorithm, the core logic for calculating eclipse timings and magnitude, it's still remarkably similar.
So we're still using the idea of effective radii based on sums and differences.
Essentially, yes. We still relate those radii to the minimum separation using Pythagorean principles to find the path length.
And still divide that path length by relative velocity to get time.
Yep. And magnitude is still fundamentally about the ratio of the overlap to the size of the eclipsed object. The inputs are vastly more precise, and we include more effects. But the basic geometric and kinematic framework, a lot of that goes right back to people like Aryabhata and the Golapāda.
It's kind of humbling. The core math behind predicting these amazing spectacles was being worked out so long ago. It really shows the power of observation and mathematical reasoning.
It really does. It connects us across centuries to these early scientists trying to make sense of the cosmos using the tools they had.
So this deep dive has been fascinating. We've really unpacked how Aryabhata used these effective radii, Sthityardha and Vimardārdha, and combined them with geometry, specifically the Pythagorean theorem, and a relative motion.
the Vikṣepa.
Right. To figure out not just if an eclipse would happen, but how long the partial phase would last, how long totality or annularity might last.
And even the Grāsa, the magnitude, giving a measure of how much gets covered up. We've gone from the why and how big to the how long and how much.
But, you know, there's still a bit more to the picture, isn't there? We know the timing and the size now, but what about how it actually looks? Like, where does the shadow start on the moon or sun?
Exactly. We haven't touched on the orientation of the eclipse yet, or, for instance, why does the moon often look red during a total lunar eclipse?
That's it.
Aryabhata had thoughts on these too.
Ah, okay, so there's more in the Golapāda about eclipses.
Yes, the concluding verses of that section deal with these more visual and practical aspects. We'll look at Valana Vielana, which describes the orientation, the point of first contact, and how the eclipse progresses across the disk.
Valana. Interesting.
And we'll explore his ideas about the moon's color during totality, plus some notes he included about visibility from different places on Earth, really completing his whole shadow theory.
Cool. So next time, we're kind of putting the finishing touches on the eclipse puzzle, according to Aryabhata. Can't wait.
It ties everything together nicely.
Yeah. So until then, here's something to think about. We've seen the incredible precision possible with these ancient calculations, based mainly on observation and math. No telescopes, no computers. What does that really tell us about, maybe, the fundamental human drive to understand our universe and the sheer ingenuity of these early astronomers? Something to chew on.